wonder what's actually happening when you pour an agarose gel that you can then use to separate pieces of DNA? Well, agarose is a sugar, and basically you dissolve the sugar and you have to heat it up to get it to dissolve and disperse and stuff. But then the fun happens, and these sugar chains kind of like knit themselves up. You can think of them kind of like yarn knitting. And to form this gel mesh. So a gel is basically a network, the solid network where you have like water in it. There are different modifications that can be made to agarose to change the like melting point of the gel, and it's really cool in that it exhibits this thing called thermal hysteresis, where basically you have to get it hotter in order to melt the gel than you do. Then you have to cool it in order to get it to gelify. So there's like different gel sol and sol gel transitions. We'll talk about this stuff. There's also this thing called Syneresis, where basically you might have seen this if you had like a cheesecake or something, and after it gets like liquid on top and it kind of shrinks down. So you can think of that kind of as the gel kind of rearranging itself a little and pushing out a little water. And so these agarose gels can do that too. And so yeah, so there's some cool stuff to talk about with agarose. Let's start with what it is. Let's start with what agarose is not. Agarose is not the same as agar. Agar contains agarose, but it also contains other things. In particular, this sugar called like agaropectin. And so when we talk about agar, we're typically making like LB agar plates for which we're growing bacteria on. But we're going to be talking about agarose, which is what we use when we make these like agarose gels that we can use to separate DNA fragments by size. And why it's so useful for this is because you can make this gel mesh, where basically you have a mesh is where you have like a infinite network of various like polymers. So a polymer is like a long chain of repeating similar subunits. And so with a mesh, you have basically this like infinite network of polymers, and it is holding some sort of liquid. And so in this case, water. And what's really cool is that this is going to allow us to send our DNA swimming through that liquid. So it's not just water, it's like a buffer. So it has like a pH stabilizer and salts and that sort of thing. But we can send the DNA traveling through the gel, and the pieces are going to get like tangled up in the gel and therefore like separate by size, because the longer pieces are going to get tangled up more than the smaller pieces. So similar to in concept to an SDS page gel, which we use for proteins, but in this case, we're using an agarose gel, and agarose gel is made up of agarose. So agarose is this like polysaccharide, this long complex sugar that's made up of repeating units of this smaller subunit, this disaccharide. And so when we're talking about saccharides, we're talking about sugars. And so basically we can talk about monosaccharides, where they're like individual sugar units, or like polysaccharides where there's a lot. And then there's disaccharides, which are like two. And so in agarose, we have a repeating chain of this disaccharide called agarose, which is made up of monosaccharides, beta D-galactose, and 3,6-anhydro alpha L-galactose. So these are just different sugars, and they're linking up, and they link up in this way, and you link a lot of them and get agarose. And so these, like all this terminology is just referring to like what's linked where. And so it's not just that they're linked any old way, they're linked in this alpha 1,3 linkage, which is important because it's going to help give it the structure. Another important thing to notice is that this guy's kind of awkward. And so it has this weird like bridgey thingy. And this is going to affect how the agarose is going to want to like shape up. So when you have agarose, when you have just like a container of like solid agarose, what's going to happen is that it is going to basically, you have these long chains. Typically they're about like 400 disaccharides or like 800 monosaccharides in these chains. And when you have it in its solid form, it's just like a solid. But when you add buffer, so when you had like your TAE, your tris acetate EDTA, basically when you add a buffer, when you add liquid, what's going to happen? Well, for basically pretty much nothing. Instead, what you have to do is you have to heat it. So for something to dissolve, we want it to dissolve, and for something to dissolve, we need to have each of those chains surrounded in a coat of water. But what's happening is that these chains are all kind of tangled up with one another. It's like we have a balled up yarn of like balls of yarn that are all tangled up together, which is not a very useful if we're trying to make a mesh. In order to get this to dissolve, to form a solution, to form this like sol, what we need to do is we need to give each of these chains, we need to untangle them and give them a coat of water. So it'll be able to get this coat of water because as we'll see, it'll be able to get this coat of water because it has all these OH groups. Basically, these are polar. So this means that like the oxygens and the hydrogens and the oxygens and the carbons, they're not sharing electrons fairly. And so atoms join by forming pairs of electrons, and electrons are negatively charged. They're counterbalanced by positively charged protons. So this is neutral overall because it has an equal number of protons and neutrons. However, because they're sharing their electrons unfairly, the oxygens are going to be partly negative and the hydrogens are going to be partly positive. And this is going to allow them to form these things called hydrogen bonds. And so we've talked about hydrogen bonds a lot in the context of like DNA and proteins and water molecules to one another. Basically, a hydrogen bond is just a special type of partial charge attraction, where where the positive partial charge is coming from a hydrogen attached to something more electronegative, so something that's hogging the shared electrons more, such as an oxygen or a nitrogen. And then the something negative is going to be a lone pair on an electronegative atom. And so a hydrogen bond is just this special type of partial charge interaction. So the important thing to know is that this is what makes water so sticky, because water has these like partial charges, and it can form these hydrogen bonds with itself. But it can also form hydrogen bonds with other things. It can form hydrogen bonds with the sugar. And this is going to allow the sugar to get coated in water. And so it's going to have to lose some of those connections to the water when it gelifies. However, it's still going to keep a lot of water, these hydrogen bonds to water. And so this is going to allow it to hold the liquid and to allow the liquid to like flow through it and to have a gel instead of just like a solid. But in order to get it to form this gel and to get it to like unclump and form this gel, we're going to need to heat it up in order to get it to dissolve, because right now it's got a lot of bonds to itself. And so remember, when we're talking about like bonds here, so it's got a lot of like hydrogen bonds to itself. It's got a lot of partial charge attractions, not necessarily hydrogen bonds, but basically it's got a lot of interactions with other copies of itself. So these aren't strong bonds like the bonds that are holding together these chains. Instead, they're just like attractions between the different molecules. And so in order to break these up, we're going to have to add heat. When you add heat to something, you're adding energy. You're allowing them to vibrate more and to break apart from one another to overcome those attractions. So this is going to allow us to like untangle our coils. And then they're going to exist as like random coils. And then at this point, so what we do for this is we take some agarose. And so typically we want to make a typical gel concentration is like about 1%. So we would add weigh out a gram of agarose, melt, stick it in an Erlenmeyer with 100 mils of TAE, microwave it in some spurts. I typically do like 15 seconds, let it swirl, 15 seconds, swirl, probably do longer in the beginning, but then towards the end, you want to make sure it like mixes thoroughly, but you don't want it to like explode off the top or anything. But basically you want to get it all like dispersed and dissolved evenly. And then what you're going to do is, so now you have this liquid, you have this solution, you have this sol. when you cool it down, you're going to take away energy. So now if it gets like, now it doesn't have as much energy in order to overcome the attractions to one another. When you cool it, so two coils are going to pair up into helices, and they do this in this anti-parallel way, kind of like the strands of DNA, except that these helices are going to be left-handed as opposed to DNA helixes, which are right-handed. When you cool it further, the helices bundle up, and the bundles are going to bunch up to form this mesh. It's kind of complicated, but like the ends of their ends are kind of like frayed, and then the frayed ends can interact with other frayed ends, and you end up with this mesh. You can add more agarose if you want to have a tighter mesh, which is good for like separating small DNA pieces. So when I talked about like the percentage of the agarose, the percentage of the gel, if you want to separate really small pieces, you want to have really small holes, because if you were to try to separate small pieces with something with really big holes, then they're all going to basically move through the holes at the same rate because the holes are so much bigger than them. But if they're smaller, then they're going to be separated better. And if you want to separate big things, you're going to want a looser mesh so they don't all just get stuck in your wells. And so you can add less agarose to get a looser mesh. So when we talk about like pouring agarose gels as opposed to SDS page gels, with SDS page gels, what we're actually doing is we're actually doing the polymerization. We're polymerizing this like acrylamide. What we're doing in the agarose, we're not doing, this is the polymerization part where all these sugar chains come together, with all these sugars come together. This is the polymerization. When you make an agarose gel, you are not polymerizing it. For polymerization is when you have like covalent bonds between things. What we're doing here is we're basically just taking these polymers that were already made, and we're just like making them orient themselves into this mesh. We're not making the yarn, we're just knitting it together. Speaking of knitting it together, sometimes you know how you like knit, if you knit, you like miss a stitch, then you have like a bigger hole. Well, what can happen is that something similar can kind of happen with your agarose gels. So basically when you're cooling the gel and when it's making this gel, it might not form like the optimal gel. So basically it'll run out of energy before it has a chance to find like its perfect happiest gel. And so what happens is your gel can kind of like shrink and expel water. What's happening is this thing called syneresis. And so basically you can think of these opposing forces. So you have osmotic pressure from like the water trying to escape, and elastic pressure from the gel wells wanting to contract. And so if you get swelling if the water is winning, if the osmotic pressure is winning, and you get syneresis if the gel is winning, if the elastic pressure is winning. And in that case, basically the water is going to get kicked out in exchange for forming some bonds between the sugar units. And so there's different, like chefs often care a lot about this because they don't want your food to like undergo this syneresis, and then people are like, why the heck is there a pool of liquid on top of my cheese? And so chefs can do things like sometimes they like use different kinds of sugars that have some like modifications and stuff that maybe make them trap more salt to make it harder, make the water want to stay more kind of to increase the osmotic pressure and decrease the elastic pressure. But yeah, so we don't really want to add those charge groups when we're running our gel though, because they would interact with the negatively charged backbone of the DNA, and we want something that's totally neutral. Speaking of this, when you have agarose, when you have agar, so when you have that agar that you use for like making those LB plates, this is actually, it has these modifications, including these, because it has agaropectin as well as just agarose. Agaropectins, like shorter chains, they're modified kind of randomly in charge. So this is kind of like a less pure type of thing, less consistent in the composition. But it has a lot of modifications, including sulfonyl groups, which are going to be negatively charged. And this is going to make it bad for our gels because of the negative charge of the DNA and the fact that we're separating, using that negative charge to propel the DNA through the gel. But it's fine for working for making these LB plates. And so that's one of the differences between the two. There are modifications that we can make to agarose, though, that don't affect its charge, that don't make it charged, but that do affect other properties. And one of these we can do is we can add like groups that'll lead to it to have a lower melting point. So we can knock that like low melting point agarose or LMPA. And so as the name suggests, it has a lower melting point. So why would you want a lower melting point? Well, one reason is if you're trying to actually do like a gel purification, where you're actually trying to take the DNA fragments out of the gel rather than just look at them. To do that, you basically like cut the band around, like cut the gel around the band. You run your gel, you see the band, you cut around it. Often this is done with great care, with like, because it's like UV and stuff. And so you have like a box and then use caution and stuff. But you cut around the band and then you want to get the DNA out. So you basically want to melt the gel. But your DNA is typically like double-stranded. And if you've done like PCR, you know, like if you melt the DNA, like you heat it up to separate the strands. Well, if you wanted to heat it up to melt the gel, you want your gel to melt before your DNA melts, basically, because you want to keep those DNA strands together, but unknit the gel. And so one way to do this is with using a low melting point agarose. But make sure you're not using a low melting point agarose if you don't mean to be using it. So in undergrad, I learned the hard way that you really, really need to carefully read the labels of what you're using. When I was accidentally using low melting point agarose instead of normal agarose, and it was my first time running these gels, and my gels were falling apart, and I was terrified and thought that gels were always going to be that bad. But no, they're not supposed to fall apart like that. It was low melting point agarose, and it was really, really old. But anyway, so just remember to read read the labels. But so how do they make this low melting point? Well, remember how the interactions we're going to get between the strands are largely based on like these hydrogen bonding between these OH groups. What we can do is, if we think of those OH groups as kind of feet, we can make modified chemical boots that we can put on them, and they're going to hide these OH groups of the. But if you add like a methyl group, or if you add like a hydroxyethyl, what this is going to do is basically you're adding more of these carbon groups, decreasing the polarity, making it bulkier. So it's harder for them to get closer together. So overall, this is going to make these less sticky. And so you're going to get this weaker mesh that's going to melt more easily. And so this can be good for when you're trying to do like a gel extraction. A cool thing about agarose and this like sol gel transition, where it's going from like the solution to this gel, is this thing called thermal hysteresis. And it's really helpful too, because basically it comes in handy in the lab when you dissolve your agarose. So you have this solution, and now you want to pour it in to make your gel, and you don't want it to gelify before you're ready. And this thermal hysteresis, basically what it means is that there's a difference between the temperature at which you're going from the solution to the gel, the solve to the gel, and the temperature at which you're going from the gel to the sol. And so you're probably familiar with the idea of basically the amount of energy that molecules have is going to determine what state they're in. As in terms of like solid, liquid, or gas, this is going to depend on the molecules and how sticky they are for one another. But basically, because you have to add energy in order to get them to overcome the attractions to one another, you add energy to a solid, you get a liquid, you add energy to a liquid, you get a gas. And so when we think about like a melting temperature, we're typically thinking about when you're going from like a solid to a liquid, and then you would expect that to be the same as when you're going from a liquid to a solid, because they're just like two directions, right? Well, things get tricky when we're talking about this sol gel, because these directions, this is actually going to involve thermal hysteresis, basically meaning those two temperatures are going to be different. It's not just the same. And so what you can think about is, so the temperature at which it melts is going to be higher than the temperature at which it gels. So why is this? So you can think about it basically when it's in the solution versus when it's in the gel. When it's in the gel, it is going to need less energy. It's going to have less energy. Basically, it's not moving. It has all these attractions that it can't overcome, and so it's in this gel form. But it's also in this very like knit way, kind of. And so it's harder for, if you had the same amount of energy, so energy basically like how much these molecules can move. If these are all just like single strands hanging out like far apart from one another, then even if they have the same amount of energy, they can be moving around a lot more than if they're already stuck in this like gel form. So when they're in this gel form, it would take a lot more energy in order to come apart from one another than if they're already apart from one another. And then they're just like, they can move all around, whereas here they can't really move all around. It's harder to overcome all of these attractions. And so if you're trying to go from the gel to the sol, you're going to have to add more heat than if you were trying, then you would have to take away heat in order to go from the sol to the gel. So if you want to go this way, if you want to take a sol and make a gel, you're gonna have to cool it down to about 40 degrees Celsius. But going the other way, if you want to go from a gel to a sol, now you have to heat it about 90 to about 90 degrees Celsius. And so now we have this wiggle room where we can boil this, we can make our solution, and then we can have it, we can like pour our gel without it solidifying first. So this thermal hysteresis comes in helpful. So basically you can think of it, it's like it kind of has a memory of where it, another place you might hear about hysteresis is like with magnets. So sometimes like magnets, if they have to align like little parts of their magnetic parts to like the magnetic field. And what happens is that sometimes like some of them get stuck, like after they magnetize, they like in one direction. And then once it demagnetizes, if they are stuck, then when you apply like an opposite magnetic field, it's going to take more to get those unstuck, kind of thing. And so basically there's like a bit of memory as to what the previous state of that magnet was. So this is used in some like tech stuff. And so when you're trying to figure out information about hysteresis, you often get links to stuff like that, which is cool, but not what we're talking about here. So though we usually talk about using like polyacrylamide gels for separating proteins, like in an SDS page, and then like agarose gels for separating DNA. But we actually use agarose to separate proteins by size in this technique called size exclusion chromatography or gel filtration. And in this case, it's this form of column chromatography. So we're flowing the protein mixture that contains our protein through this column that's filled with these little beads that are going to separate it by size, because these beads have these pores that are going to affect their travel. And these beads are sometimes often made of agarose or similar modified forms of agarose and that sort of thing, or dextrin, various things. But the agarose is really good for this because it is neutral. Like it's one of the reasons why it's good for the DNA gels. And so they often like use, but it's also like we don't want it to melt, we don't want it to squish, all of these things. And so it also has like modified forms, and it has like cross linkers that are going to help actually cross link these chains together as opposed to just being knit together. So cool stuff. And there's a lot of places you'll see agarose if you are doing biochemistry.